So here's the finished product. Again, this surface would be an involute. There's an airfoil nose, and then this surface in the inside here is also an involute. It didn't seem to have a lot of starting torque. Once it got going, it did pretty well. Just didn't seem to start that well. I wasn't impressed by the tip speed of it. It just, our wind wasn't super strong, but it seemed to me like it could be going a little bit faster. It did seem pretty smooth. I mean, it would rotate, and I didn't feel much pulsation as far as pressure or anything like that. It seemed like it was running very smoothly, so I was happy with that. I don't think this would be my final design, but I just wanted to throw that idea out there as far as pressure on the surfaces and that sort of thing. I don't know if that would be optimal. Maybe it'd just be better to have, you know, a scallop here so that you get pressure with the maximum radius possible. That might be even better. I don't know. But it's just an idea. I wanted to use a curve called an involute in this design. An involute curve can be generated if you imagine a cylinder and you wrap a string around that cylinder, and then if you pull the string over here and start unwrapping it, keeping it tight, you would generate a curve something like that. And the interesting thing about this curve, like if that's the string, any place that you apply pressure to this curve, that force from that pressure is directed to the tangent of this circle. So if I have a wind turbine and the wind is blowing against this surface, then it's going to apply that force at some distance from the center and create a torque. It's also used with gear teeth. Usually in this region here, you have gear teeth, and they keep a... the nice thing is it makes the gear teeth run smoothly because the forces are always applied at a constant distance from the center. Anyhow, it's not too hard to describe this curve mathematically. If this is the radius of the base circle, that's what this would be called. And this is the point of interest. And we'll call this distance r. And they do things with polar coordinates in this. I'll use the variables names that were in this website that I saw. This total angle here would be theta. I'll just write it down here, theta. This angle here, from here to here, they called INV alpha, and I think that means involute alpha. And this angle from here to here, they just used alpha. Let's stick it up there. Okay, so what we want to do is with polar coordinates, if you specify a distance and an angle like this INV alpha, you can define where this point is on that curve. this is tangent to the circle, so this is a right angle here. So we're going to specify this R, and then we're going to find what the I and V alpha is. So we're going to assume that R is specified and the corresponding angle is what we're going to find. And if we knew this full distance theta and we knew this alpha, we could subtract that alpha from this theta and we can get this I and V alpha. Turns out we can do that because this length here is just the amount of string that we've unwrapped from the circle, and that amount is R sub B times the angle that we've unwrapped, which is theta. Okay, so here we go. I and V alpha is going to be equal to that full angle theta minus alpha. This is a right triangle here, and we can find what alpha is because the side adjacent over the hypotenuse is going to be the cosine. So we know that the cosine of alpha is equal to R sub B over this R, or alternately we can just write alpha is equal to cosine inverse R sub B over R. Okay, so we found that alpha, and then the remaining problem is finding this theta. And so we can find that theta too because we know what alpha is now, and we know that alpha, or the tangent of alpha, is the side opposite over the side adjacent. So tangent of alpha is equal to the side opposite, which is R sub B theta, over the side adjacent, which is just RB. And so tangent of alpha is equal to theta. So we have I and V alpha is equal to the tangent of alpha minus alpha. Okay, this is a different angle here. This is just one thing, I and V alpha. So we find alpha, or we specify an R that we're interested in. We can step through different R's. It's kind of like going on an X and Y graph, just doing different X's and plotting the Y's. And we specify the R. We know what our base radius is. That's our design variable. We can find alpha, take the tangent of alpha, and then subtract alpha, and we get I and V alpha. So we know what this angle is from here to here. Now if we look at this as Cartesian coordinates here, y and x, we can convert this polar expression into x and y. We just say x is equal to r, this distance, times the cosine of I and V alpha. So that's this distance here, if you brought this down here, that distance. And then y is just equal to r sine I and V alpha. So we can find xy coordinates of this involute curve. So specify r, calculate alpha, find I and V alpha, and then express it in x and y coordinates. Just a couple other quick details. Normally the curve just comes off like this. If I wanted to reverse that and bring the curve off this side, what I did was I just put a minus sign in front of the x value here so that it just did a mirror image of what was on this side. So just added that to be, to change the direction. Also, another thing that I needed to do is sometimes I wanted it to to start a little bit up instead of coming off right from here at the 0 angle. I wanted it to start here and go. So if this was some offset like alpha 0, all I did was I just added the offset value here to the X and Y. So there are just some quick changes just to be able to position this this involute right where I wanted it. So this changes the direction, and this just rotates. The alpha 0 just rotates the curve, plus or minus. And everything is in radians, just to be clear. The way I plan to use this in my vertical axis wind turbine was to start out here. I wanted some sort of a nose here, so I just took a part of an airfoil. So I just kind of took an airfoil nose here, and then I put an involute curve here and a second involute curve here. This involute curve was directed at a base circle here. There's a little larger involute, or a larger base circle for this involute. This one was directed on this side of the circle. So pressure here would be directed to the right of center and create a torque in this direction. And pressure on this surface here would go this direction and be directed to this circle kind of on the left side, and also create a torque like that. And then the nose was supposed to just minimize the drag as it came around. So anyway, the idea was that anywhere you touch this wing with pressure, it's going to create a torque, except for the front, of course.